around a banked turn. So let's call this banked turn physics. Okay, so the idea is, imagine that you have a curve in a road. That is not at all a curve. There we go. Okay, and you are coming into this curve here, and you are exiting this curve over here. Like that. Okay, so you have to imagine that we're looking at this from the top down, and our car is traveling along the road here. It's going around the circle, and it's exiting here. Okay, this is the radius of our curve. And, you know, if this were just a flat curve, you would know that the force, the centripetal force allowing this object to turn, right, to deviate from its inertial path, which would tend to take it straight, is provided by friction. Okay, that's the only force that can provide that without having a bank turn. However, in certain circumstances on certain highways, you might get snowy winters where the frictional force is very low, and in those cases, you tend to find a bank on the corner. You see this really obviously in things like velodromes where bicycles ride around the corner, or NASCAR, or something like that, where you know, vehicles are going really quickly around a corner, and friction alone would not be enough to hold the vehicle on the road. So the question is, what physics are involved in getting this thing to go around the corner? So the first thing we'll do is we'll look at a standard situation like we may have seen before. We'll have our object, our mass, our car, represented as a block, like that. And we have looked at these types of problems before, where you just have a static object sitting on a surface. So in a case like that, we would have set it up such that we have, you know, a gravitational force aiming down. This is causing a normal force to be present up in this direction. Let's just fix that. So, and what we would do is we would say, okay, well, let's find the sum of these vectors, okay, and set it up like this. So this is for a static object sitting on a slope, right? Now this is not the situation, right, that we have. So what this would end up with, actually, just before we move on, is if mu equals 0. In other words, if there's no friction, this object has to accelerate down the slope, okay? And the force mediating that is sort of the resultant of gravity and the normal force interacting, causing this resultant force that causes an acceleration down the plane. This, of course, grows as the slope gets larger and decreases as the slope gets smaller. And when the slope drops to 0, the acceleration is null. When this, you know, increases to 90, then the acceleration is just straight down at g. Okay, so this is the standard situation where you know, an object is just sitting still on a surface. But now we have something different going on. So we have to rethink the mathematics involved here. Okay, so now what we have is we have an object traveling around a corner, and let's just say we take a snapshot of it when it's right here on the banked curve. Okay, that's what we're looking at. It's coming zipping around the curve, and we take a snapshot of it. This is towards the center here. For goodness sake. This is towards the center here. Okay, this value here is the radius to the center. All right, and this is our bank angle. All right, so what we're going to do is we're going to move some things around. Now we have an object that is essentially sitting statically on this surface. If we just took a snapshot of it, right, we'd realize that there's no accelerating force towards to have it slide down the slope, and no accelerating force having it slide up the slope. It's stable here. Okay, so the net forces acting on this object must be 0. So the question is, what's different about this? Well, the first thing that's got to be different is the normal force is larger than the normal force would be if it was just sitting on a surface statically. Okay, the reason for that is that the object has inertia, right? And so the normal force has to supply some sort of force towards the center beyond just the amount of normal force that's required to, you know, counteract gravity, or that is a result of gravity. So this normal force is going to be larger than it would be if the object is just sitting still. Okay, so now when we think about that, we have to look at the components of this normal force to explain what's going on here. So you still have gravity, and it does play a role here. Okay, so there's still going to be gravity acting on this object called Fg. We know that's equal to mg. Okay, but the object is not accelerating in the y plane. So what that means is there must be a force equal and opposite to gravity in the upward direction. Let's just draw that on this color. Let me get this color here. And this is a component now of the normal force. All right, so we can transfer our theta value into here. How do we know that that's true? Well, if we extend this line down, we draw 90 here, okay, and we say put a value called say like alpha right in here. Okay, this then becomes alpha. This is a 90. This must be therefore theta, and then by interior angles, this is also theta, right? So theta gets transferred up into here. So we get essentially similar triangles between this and this guy up here. All right, so then we say this side is equal to mg, equal and opposite to mg, but it's also a component of the normal force. So it's the normal force, which becomes the hypotenuse, times the cosine of theta, because it's the adjacent angle. So mg is equal to Fn cos theta. Okay, and another part of this normal force is actually going to provide the centripetal force. So there it is. Here's a force aiming towards the center of the circle. Okay, we call that Fc, and that is found as Fn times the sine of theta. Okay, so that's the sine of theta, right? Fn opposite angles, Fn times the sine of theta gives us the centripetal force we need to go around the circle. All right, so that's sweet. Now, what we would know about this object is that it is got a mass, okay, and we know that that's mg. So we should be able to do a little bit of math right now. We should be able to say this. We should be able to say that the tangent of the theta value is equal to the opposite over the adjacent. The opposite over the adjacent. So it equals Fn sine theta, okay, divided by Fn cos theta. But actually, that's not exactly useful to us. Let's just do a rewrite. If this is equal to Fc, we should be able to say then that mv squared over r, right? That's our Fc value, is equal to Fn sine theta. Sort of because this is getting a little bit like crowded here, let's just redraw this triangle just to help us understand here a little bit better. So again, we've got our normal force like that. We've got the component of the normal force counteracting gravity like that. We have our centripetal force here. Okay, so this must be equal and opposite to mg, and this must be mv squared over r, right? As we sort of defined there before, and this is theta. So tan theta is opposite over adjacent. So we could say then that tan theta is equal to opposite, which is mv squared over r, over adjacent, which is mg. And we can do some algebra on this. So we're dividing this by this, which is the same as saying, you know, mv squared over, let's bring this up, right? Because we're going to divide by this, then divide by that. So we can just divide by the product of all of them. Rmg, m's cancel off, and we're left with this. The tan of theta must be equal to v squared over gr. It's not usually left in this form. We would probably rearrange it to this. V squared equals gr tan theta. Or, oops, if you want, v equals root gr tan theta. So what this is telling us is what velocity I can take a turn of radius r with a bank angle of theta. Okay, the perfect speed that I can take that at. If I go any faster, I would tend to slide up the slope. If I go any slower, I would tend to slide down the slope. Actually, just examine that quickly before we wrap up. Why do you tend to slide up the slope as you go faster? If you look at the formula, and actually, sorry, let's put a curve in here. Got this curve here. You got your R value, okay? You're coming in at some velocity, and let's say you try to take it at a higher velocity, and you have zero friction, okay? Well, if you think about it, the centripetal force is set by the angle we have here, right? How much centripetal force we get is set by whatever angle we've put here. You can't get any more, right? The only way you can get more is by changing the angle. So that's set. We know that it's equal to mv squared divided by r. So as this increases, right, the radius of turn must increase. Well, as you move up, your distance from the center also increases. So you have a small radius to the center when you're on the inside of the track, and you have a larger radius to center when you're on the outer side of the track. So moving up here just creates a larger radius. Now this is kind of like a self-correction, right? As long as the track's wide enough, right, your height up the slope will be dictated only by your velocity. So this actually leads to another physics problem where if you're driving around in a circle inside a cone, an inverted cone, right, the velocity will dictate where on this cone above the bottom you reside, depending on what your theta angles are. Okay, but that's a different kind of problem. You often see that with motorcycles or something like that, right, riding around inside a cone. The other way to think about this too is that this object tends to want to go straight into the page, right? What is making it turn is this slope angle, right? So if it's going faster, you're fighting harder to change or to cause it to accelerate towards the center, right? Anyway, we'll just leave it at that.